We're going to take a look at volumes from the shell method today. So volumes of solids of revolution. Last time we looked at disks, and today we're going to look at shells. Surface of cylindrical shells unwraps to form a rectangle. If the radius of the shell is x and the height is f of x, the area of the rectangle is x times f of x. And we can see that because if we look at these pictures down here, if we have some sort of curve y equals f of x and we're rotating it around the y-axis, what we end up having is we have some sort of rectangle that has a certain width, which eventually, as we do all of them, the sum of all of those widths, as we make them really, really close to zero, we'll end up getting everything as we move along. But we're taking this rectangle and we're sweeping the rectangle around the axis, and it ends up going in the backside too. So we end up with basically a cylinder going all the way around, and we add up all of these cylinders and it turns into the volume of the entire thing. So you can kind of see that in this picture. And then this picture is what happens if it's not rectangles, but it's basically the entire thing that's kind of getting shaped around. Shells are always parallel to the axis of rotation. So this is an important note that we have to keep in mind. If we are doing disks, it is perpendicular to the axis of rotation. And if we are doing shells, they are parallel to the axis of rotation. So if we can be a little playful, we can say that disks are perpendicular or perpendicular to the axis of rotation, and shells are parashell to the axis of rotation. So that might help you remember if you need a little reminding. Okay, so the general form for finding the volume of this, remember we are doing cylindrical shells as we're going along, so we're basically taking this rectangle that we have here and we're rotating a rectangle. So if we're rotating a rectangle all the way around, what we're going to do then is we're going to treat it like we have a base and a height. And then since it's a cylinder, if we're finding the surface area of this cylinder basically going all the way around, the formula for that is 2 pi RH. So since we have 2 pi RH, R is this little b and h is the height. So in this case, we have 2 pi, and then the base or the radius of each of these things is x down here, and then the height is f of x. So if I have a shell method, I'm going to do 2 pi times the integral from a to b of x times f of x dx. That's typically what ends up happening. And over here, it's 2 pi times the integral from a to b of y times f of y dy. Notice that if we're parallel to the y-axis, that means we're parallel to x equals a number. And if we're parallel to the x-axis, that means we're parallel to y equals a number. So we're ending up with, if we're rotating it around the y-axis, we actually do things in terms of x in this particular problem. Now, in general, not with the x's and the y's or whatever, it's 2 pi times the integral from start to finish of the radius times the height times dx or dy or whatever it is. So we have to make sure that we keep track of what r and h are as we move along. Okay, we're going to use shells to find the volume generated by this and the x-axis. So if I quickly sketch this, it's going to look something like that. And if I want to go from x equals 2 to x equals 9, I'm taking this area and I'm sweeping it around to the other side. And each of these, basically, if I kind of look at it as if I have a small rectangle and I want to sweep that around, I end up with a cylinder that goes all the way around like this, and I would repeat the process for every single cylinder of rectangle of whatever width it is, and then as we take the width as it goes to 0, we end up finding the exact volume of this going all the way around. But I would repeat the process for the next one and the next one and the next one moving along. So it ends up with another cylinder that just kind of tacks on to what I previously had. And so as you expand it, you kind of add layers and add layers to it, kind of like you see here. If I use shells to find the volume of the region bounded by y equals x squared and y equals x, so what I want for this is the integral from 2 to 9, and then I have 2 pi, and then I look at what is my r in each of these cases, and my r is always, as I'm looking here, my r is this length. So my radius goes from where I'm rotating around to wherever I'm starting, and so that's the radius of this. And then if I went to the next one, the radius would be a little bit bigger and so on. So r appears to be x, and then my height appears to be f of x. So in this case, that's 2 root x. And then I have dx. We see that we have this area that we're going to sweep across going to the other side. And it'll end up being some kind of, it basically will look like an angel food cake essentially, or a bundt cake or something, where if you sweep it across, you'll have this little hole in the middle, and then a bunch of cake basically on the outside. So if we do 2 pi times the integral from 2 to 9 of x times 2 root x dx, we get about 1193.017 for our answer. And then I confirmed it using the disk method. Now notice the disk method on this problem would be really, really difficult because you would have to break it into 2 different cases at this line, because you would have from 0 to 2 square root of 2, it's 9 squared minus 2 squared for our two radii. And then for the second part of the problem, it's 9 squared minus y squared over 4 squared, because you would have to change it to be in terms of y's in order to do this. Um, but the biggest radius would be 9, and then the smaller radius would be um, y squared over 4. And so that would be how you do problem 1. Use shells to find the volume of the region bounded by y equals x squared and y equals x. So if I have y equals x squared, y equals x, and then I revolve this around the y-axis, each of these rectangles is going to get revolved around, and I form these little shells, these cylinder shells, and that continues to go around for each individual one. So I'm going to take the integral 2 pi, and then I need to figure out what's actually happening. So with my radius and my height. So this is going to be in terms of x. So I'm going to go from 0 to 1. That's because the intersection point here is 1, 1. So I'm going to go from 0 to 1. And then my radius always appears to be whatever the length of x is. And then my height, well, my height appears to be from y equals x down to y equals x squared. So my height appears to be x minus x squared. So that is the shell method for that problem. If I take this exact same picture, but instead of rotating it around the y-axis, I rotate it around, and this won't be drawn to scale, but if I rotate it around y equals 4, or I'm sorry, x equals 4, what's going to happen is I have the exact same rectangles. So all of these rectangles are going to end up being the same. But when I rotate it, it's going to go way around over here. So I'm going to have this same rectangle that I had over here, but it ends up getting swept over a much, much bigger portion of space, and so therefore the volume should end up being a lot bigger. So I have 2 pi times the integral from 0 to 1, because I'm still, my x's are still 0 to 1. But now I need to figure out what r and h are in this case. And so r, the length of the radius is going to be, it appears the length of this radius is 3. The length of this radius is a little bit bigger than 3. And then once I get all the way down to here, the length of this radius is 4. So my radius has to be between 3 and 4 all the time. And so what it appears is that the radius is 4 minus x. And that makes sense, because if I take this line and I subtract whatever x is, then I end up with 4 minus x is my length of the radius. So 4 minus x is the length of the radius. And then the height of my rectangle is exactly the same as it was in the previous problem. I don't know what just happened. It's the same length as it was in the previous problem. So that is x minus x squared. So I have 4 minus x and then x minus x squared dx. Problems 2 and 3, we have y equals x squared and y equals x. So we're taking this section and we are rotating it around the y-axis. And when we rotate it around the y-axis, 2 pi times the integral from 0 to 1 of x times x minus x squared, because remember the radius is x, and the height is x minus x squared, we end up with about 0.524. And I showed that it is equivalent using the disk method, because in the disk method I would have to have y's. My big radius would be square root of y, and my small radius would be y. Um, so that is what would happen in problem 2. Problem 3, we would be revolving it around the line x equals 4, which is way out here. We would take this thing and it would go all the way over, it's even further than that. Uh, the other side of this cylindrical looking shape where there's a giant hole in the middle would be over here, and then it would come way out of the screen kind of towards you. It's a giant 3D shape. That volume would be about 3.665. And if we look at this, the radius is from 4 minus x. So, for example, at about where my mouse is right now, the radius would be about 3.4. So that's 4 minus 0.6. Y equals root x over 0 to 2. And then it's also bounded by the y-axis. So this is my area that I'm looking at. So notice that the y value goes up to 4. This problem is actually probably easier to do by disks, so let's do it by disks first and then figure out how to do this with shells. So if I'm rotating it or revolving it around the x-axis, if I revolve it around the x-axis and it is in terms of y equals f of x of some kind, that means that this is actually set up for disks. So I have to do pi times the integral from 0 to 2 because I'm having my rectangles perpendicular to the axis of rotation. And so then I take this and it sweeps out some sort of disk. This is actually going to sweep out a little bit of a washer here because there's going to be this part in here that doesn't have any sort of volume to it. But as I sweep that out, I figure out that my radius, I actually have a big R and a little r that I have to take care of. So my big R is 4. The radius of the line from 4 down to 0 is always 4. So this is pi times the integral from 0 to 2 of 4 squared. And then little r that I'm basically subtracting from that is whatever the height of y equals x squared is. So that's x squared squared. So this should get me the answer in terms of disks. In terms of shells, it's going to be 2 pi times the integral from, if I'm rotating it around the x-axis and I want to do this in terms of shells, that means that I need to have rectangles that are parallel to the axis of rotation. So that means I actually need this to be a function in terms of y. So I'm going to take y equals x squared, and I'm going to turn that into x equals square root of y. Notice that it is positive square root of y, not the negative square root of y, because it's in the first quadrant. So remember, when you take a square root, you have to do plus or minus, but in this case, we're going to take the positive case. So now I have to figure out what my r and h are in this case. So radius is going to be from the line of rotation to wherever my value is. So the radius appears to be y. And then the height of my figure is the square root of y. So I get y squared of y dy. Now my bounds have to be in terms of y, so that's going from 0 to 4. So this is the shell method, and then this is the disk method, and they should end up giving me the same answer. Problem 4, we have this area, and if we use disks and shells, we get the same answer, which is 80.425. I explained it pretty well, I think, when I was writing it down, so I don't need to go into too much detail on the Desmos part of this. I hope you enjoyed the video today.